Okay friends, welcome to the third lecture on acoustics and noise control. So, we have been taxing for a while, we have been giving you motivational stuff as to why the topic of acoustics and noise control is a very important topic in today's engineering community. We will dig deeper today. So, just to recall, we understood that the cause of the perception of sound is the pressure fluctuations which are impinging on our eardrum, and the pressure fluctuations are conveyed from the sound source to the receiver within the ambient fluid medium, which in this case as we are talking is the air. So, in certain naval applications obviously this fluid medium could be water. So, the question of transmission is of this sound is essentially boiling down to the question of how the pressure fluctuations are getting transmitted from the source to the receiver, and it so happens to be in the form of wave. What is a wave and how do we arrive at this conclusion? We will see that right in today's class. Okay. And just a few common things. It is well known that sound wave speed in air is about 340 meters per second. It does change a bit depending upon temperature, atmospheric pressure and so on and so forth. So, we will see to it that how this sound wave speed is derived. So, this is something that we at this point take it as an elementary fact that we just believe in, but we will derive it soon enough. Okay. So, the pressure fluctuations are not just an isolated phenomena. So, the pressure fluctuations are accompanied by density and velocity fluctuations in the medium. So, there are density fluctuations which essentially mean that the fluid now essentially is not an incompressible fluid, but a compressible fluid, because you have to accommodate for the fact that the density is going to change as the acoustic waves are going to travel. So, pressure fluctuations are accompanied by density fluctuations for shear and velocity fluctuations in the medium. Fluctuations themselves are being conveyed in the form of the wave within the acoustic medium, and they are travelling at the sonic speed, which basically means the sound wave speed. Numerically the value is near about 340 meters per second. So, therefore, the perspective that we will look at is that the sound transmission within the fluid medium, in particular air, is just a special case of fluid dynamics. It is a fluid dynamic phenomena because of which the sound is travelling from one point to another, at least within the air. We are not talking about structure borne sound, at least for now, but we are talking about the transmission of sound from the source to the receiver. This is basically the transmission of pressure fluctuations accompanied by a density fluctuations from the source point to the fluid to the receiver point. Accordingly, we will treat acoustics or sound transmission, more specifically sound transmission, to be a special case of the fluid dynamic equations, and that is how we will derive the governing equations of acoustics in the present class. So, acoustics we know is a study of various issues related to sound, but we also understand from this argument that it is a special case of fluid dynamics, wherein the flow variables are small oscillations over the mean values. Remember, that is the perspective we had right from the first class, that over and above the atmospheric pressure there are some small fluctuations which is basically hitting your eardrum, that is how you are hearing my voice. So, these small fluctuations are the acoustic quantities of interest. The fluctuations will be in the form of pressure, will be in the form of velocity, will be in the form of density, and we will, since there is a density fluctuation which we are going to trace out. So, these density fluctuations can be accommodated only if we have a model of the fluid dynamic equations as that of a compressible fluid flow rather than an incompressible fluid flow, and incompressible fluid dynamic equations will not be able to cater for fluctuations in density. So, therefore, the perspective that we will adopt from here on is that the acoustics is a special case of compressible fluid dynamics or compressible fluid flow. But unlike a true gas dynamics course where the these density fluctuations can be of any erratic fashion, what we have sort of laid down is that these density fluctuations are necessarily small. What do I mean by small? I will come to it in a moment, but at least in colloquial terms it is small in comparison to the mean value, and I have some numbers to show you as to what I mean by that. So, essentially what I mean is that all the flow variables, namely pressure, velocity and density, can be decomposed into two parts, one which is the mean component and the other which is the small acoustic, oscillating or fluctuating component, right. So, that is how we will treat all the variables that arises in acoustics. Over and above the mean value, there is a small acoustic oscillating component, and it is the small acoustic oscillating component, the magnitude of this oscillating component, that we will try to track, we will try to figure out what the implications of these small fluctuating components are, and that is the acoustic quantity of interest. So, that is the agenda for the day. Just to give you a feel as to what the order of magnitude of different variables are, considering a very intense sound source of 100 decibels, which is like very close to a, let us say, an aircraft engine, you will hear this kind of sound. It is something which is rarely heard, and thankfully so, that it is very rare that you will hear sound of the order of 100 dB. So, in fact, you should not be exposed to a 100 dB sound in normal day to day life, but a very intense sound of 100 decibels will have a mean component for this sound. If we now try to decompose the fluid dynamic variables into two parts, the mean component and acoustic component, the breakup goes in this fashion. For the fluid pressure, there is a mean pressure which is 101 kilopascal, effectively the atmospheric pressure, right. The atmospheric pressure is 101 kilopascal. So, the mean component of the pressure is 101 kilopascal in this case. The acoustic component is just 2 Pascal, right. So, which means it is 2 divided by 100 into 10 to the power minus 3, that is the ratio between the acoustic component and mean component. It is very, very small. Okay. Similarly, if you look at the density of air roughly is 1.2 kilogram per meter cube in standard conditions, but then even due to a 100 decibel intense sound, the acoustic component is that much, and it is up fifth decimal place that you get to see a significant digit. So, it is pretty small, this acoustic component is pretty small in comparison to mean component, right. Similarly, if you look at the velocities, if velocities in air, even if it is a severe cyclonic storm, it can go at the most of the order of 100 kilometers per hour, but the acoustic component can rarely go more than 5 millimeters per second. So, 5 millimeters per second is all that you have in terms of the velocity of the fluid particles as it is oscillating. But yes, if you really consider a quiet room of the sort of this recording studio, then the velocities can be assumed to be nearly 0, that there is no mean flow in this room. So, the mean component of the medium that we are talking, it could range from 0 in a quiet room to a very large value which is happening in a cyclonic storm sort of a case, but the acoustic component none the same remains small. Okay. So, suffices to say that acoustic pressure, acoustic density and acoustic velocities are all small quantities in comparison to the mean quantities. It is only under a quiet room assumption that you get to see the mean component of velocity to be also 0, in which case you just do not worry about the mean component, but in some aeroacoustic cases you are also interested to know what happens due to a bulk fluid flow, and those bulk fluid flows are definitely much larger than 5 millimeters per second. So, this will give us the cue as to how we will go about tackling this problem of acoustic wave propagation from the source to the receiver. So, we will essentially break up all our variables of interest in two parts, a mean part and an oscillating part. The oscillating part we will do a bookkeeping and we will have a way to show that this oscillating part remains small, and we will track out the equations that we get of this small oscillating part. We are not interested in the mean part, that is what is done in a course in fluid mechanics, where they will talk about how the equations of mean flow evolve, but here we are not worried about the equations of mean flow, here we are worried about the equations of the oscillating or the fluctuating part, right. So, that is the acoustic case for our interest. So, the process is this way, that there are flow variables which is velocity, pressure and density, and the governing equations for these fluid flow variables are continuity equations and momentum equation, right, something which you have done in your undergraduate classes. In case you need to refresh, please look at any book in fluid mechanics to know what are the continuity equations and momentum equations. You could possibly look at its derivation also. But what we will do is we will appeal to these equations without really going through the derivation of continuity and momentum equation. We will appeal through these equations together with a thermodynamic process for the compressible flow, because as you know, the compressible flow essentially means that there is a change in pressure as well as density. So, if you assume a suitable model for the thermodynamic process, which in this case will be assumed to be as adiabatic process, and if you make that assumption, then you will get one more equation which is the thermodynamic process equation. If you can further, we will make an assumption today that the bulk fluid is stationary or quiet, it is not having any mean flow. So, we are typically interested as of now in an ambient fluid medium where there is no mean flow, right. We are not talking about severe cyclonic storms where there are large mean flow created. We will assume that the fluid is homogeneous, that is the properties of the fluid is uniform throughout the region of interest. There is no change in density or there is no change in temperature of the mean components. There can be change in the oscillating part. When we say the fluid is homogeneous, we essentially mean that the mean density of the fluid or the mean pressure of the fluid is constant over the entire region of the fluid. It does change when the sound flows through, but that we will separately track through our acoustic equations. Okay. Another very crucial assumption we will do for now is that the fluid viscosities are neglected in the development that we will do today, which is the acoustic wave equation. So, in this development, the reason why fluid viscosities will be neglected is because the effect of fluid viscosity can be shown to be equivalent to an energy loss. That is actually pretty easy to understand, because viscosity is an energy dissipation mechanism. So, the inclusion of fluid viscosity, which is truly there, is going to induce some additional losses into the acoustic wave propagation, because of which the wave will sort of decay as it travels further distances, but the presence of this decaying aspect will be ignored. We will simply assume today that there are no energy dissipation mechanisms in the fluid, and we will try to figure out that what is the equations governing the transmission of wave or transmission of sound, as I should say, from the point of generation to the point of reception. Okay. So, using these equations, acoustic wave equation will be derived. So, let me show you the derivation. Okay. So, here we will derive the governing equations for acoustics. We will start by specifying all the flow variables of interest. So, flow variables of interest are 1 pressure. So, that we will denote by the symbol P, and we will break this up into two parts, the mean component Pm and the acoustic component or the fluctuating part, as we have said. So, this is the mean component, and this is the acoustic or fluctuating component. So far so good. Now, to make sure that we understand that the acoustic component is much lesser than the mean component, what we will do is we will introduce a bookkeeping parameter epsilon. So, epsilon is a small bookkeeping fictitious parameter, and the reason for its introduction is just to keep track of the orders of magnitude of different variables. So, it does not have any physical relevance, but we will see it will be very useful in the derivation process if we introduce this epsilon notation here. So, similarly the density can be broken down into two components, one which we will denote as rho subscript m, meaning again the mean component, plus rho a, and just as usual this is the acoustic or the fluctuating part of density, right. And again, since we know that the acoustic or the fluctuating part of density is small in comparison to the mean density, we will precede this rho a with an epsilon term. So, wherever we see this epsilon label, we will understand that it is small in comparison with other terms which does not have this epsilon component, right. And lastly, for the velocity, which is a vector, we will denote it as u with a vector symbol, and we will ignore the presence of any mean component, as we said that we are going to think that the fluid is not having any mean component, it is having only a fluctuating component. So, accordingly this will be denoted as epsilon u a, right. So, there is no mean flow in the fluid medium as per our assumption. So, with this setup, let us now look at each of the fluid dynamical equation. We will start with the continuity equation. So, the continuity equation we will recall from any fluid dynamics undergraduate level textbook is given by del rho del t plus del dot rho u is equals to 0. This is the continuity equation. So, if we substitute rho is equals to rho m plus epsilon rho a and u is equals to epsilon u a, in this equation what we get is the following: del rho m del t plus epsilon times del rho a del t is what we get from the first term, plus del dot rho m plus epsilon rho a into epsilon u a. U vector is being replaced by u a because there is no mean component as per our assumption. So, that must be equal to 0. So, we will open this up and what we get is the following: del rho m plus del t. So, derivative of the mean density with respect to time plus epsilon times del rho a del t. So, derivative of the acoustic density with respect to time plus divergence of the following quantity: epsilon rho m u a plus epsilon square rho a u a is equals to 0. So, this in turn would mean del rho m del t plus epsilon times del rho a del t plus del dot rho m u a plus epsilon square del dot rho a u a is equals to 0, right. Now, we note the following: we understand that this is an order 1 term, whereas this term, which is the square bracketed term multiplied by epsilon, since it is getting multiplied by epsilon, we call this term as order epsilon term, and similarly this term is an order epsilon square term, right. By our basic assumption, epsilon is a small number, which means that though this equation says that on the left hand side you have 3 terms and some of these 3 terms should be 0, but we realize that there is a difference in orders of magnitude between the three terms. There is the first term which is of order 1, there is a second term which is of order epsilon, that is it is necessarily smaller compared to the first term. And if you note the third term is even smaller because it gets pre-multiplied by epsilon square. If epsilon is small, epsilon square is even smaller. So, therefore, what we have here is sum of three terms on the left hand side equated to 0, but then each of these three terms are having different orders of magnitude. So, using the fact that these three terms are of different orders of magnitude, there is no possibility that these three terms can mutually cancel each other, because they are at different orders of magnitude. One is very large, the other is small, the third one is even smaller. So, therefore, the only way in which the sum of these three terms can go to 0 is by the argument that each of these three terms has to be 0. This is what we call as an asymptotic argument or an order of magnitude study. So, by order of magnitude arguments, we conclude that each of the terms, each of the three terms are 0, right, which means at order 1 we have del rho m del t equals to 0, which implies that the mean density of the medium does not change with time. Also, we have assumed the medium to be homogeneous, which implies that mean density rho m is constant over space as well. Okay. So, we have as a result rho m is constant over space and time. Right. So, this is our inference at order 1. Going back to order epsilon, what we get is the following. At order epsilon, if we look at the equation, we will get the following, that del rho a del t plus divergence of rho m u a has got to be 0. So, del rho a del t plus del dot rho m u a has got to be 0. But rho m, as we have seen, is constant over both space and time, which means you can pull rho m out of the differentiation process within this divergence operation. So, that essentially means del rho a del t plus rho m del dot u a has got to be 0. Okay. This is an important equation which we mark it as equation 1. At order epsilon square, you get another equation, but this is not of our interest. So, continuity equation basically gives us two very important inferences. One is that the mean density is actually constant over time. It is also assumed to be constant over space, because by assumption we are now dealing with a homogeneous medium. At order epsilon, we get this equation 1 as our result. Now, coming to the momentum equation or the Euler equation. Euler equation is a special case of the Navier-Stokes equation for inviscid fluid. Recall, by our assumption we are dealing with inviscid fluid for now. This equation is stated is the following: rho times du dt, and u is a vector, is equals to minus gradient of p, and du dt, d dt rather, is called the material derivative, and it has two parts. It has two parts. One is, it is simply partial derivative with respect to time plus u dot del. Okay. U dot del, you may open it up in the following fashion: del del t plus u x del del x plus u y del del y plus u z del del z, if you want to. So, this is the statement of the Euler equation, which is available in any fluid mechanics book. If you want, you can check it. So, now we will proceed from here on in our derivation for the acoustic governing equation. So, this is given as follows. So, firstly we will try to make a simplification for the material derivative. So, the material derivative du dt will be written as del u del t plus u dot del of u itself, right, the vector u itself. So, therefore, now substitute the fact that the velocity vector is actually comprising of the small acoustic component and nothing else. So, we have already defined the velocity vector to be u is equals to epsilon u a. U is equals to epsilon u a was defined. So, using this definition we will simply make the appropriate substitution in the material derivative that we see here. So, again you see that du dt therefore is epsilon del u del t plus epsilon u dot gradient of epsilon u. Okay. So, that again means that the first term is order epsilon and the second term is epsilon square u dot del u. Okay. So, therefore, as as one can understand from this derivation, this is a higher order term or order epsilon square term. So, I will put an A here. So, del u del t, the formula for del u del t will now read as the following. We will have epsilon del u a del t plus epsilon u a dot del gradient of epsilon u a. So, u a is a vector quantity. So, I appropriately put a vector sign here, and then in the next step if I simplify the second term, you will see that what I have done is I have taken the two epsilons out and this is epsilon square. So, the second term is epsilon square u a dot of gradient of u a. Now, please note that we have already said that epsilon is a small fictitious quantity. So, epsilon square is even smaller. So, as a result this second term is order epsilon square, whereas the first term is of order epsilon. So, definitely the first term is larger than the second term because it has only order epsilon sitting in front of it, whereas the second term is having an order epsilon square effect and as a result is small. So, we might as well choose to ignore the second term and write this as epsilon del u a del t from here on. So, therefore, the material derivative of u in the Euler equation will from here on be simplified to epsilon del UA del T. Del T is just the partial derivative with respect to the time. So, what we have derived is that the material derivative du dt is equal to del UA del T is equal to del UA del T for the acoustic component. That is what we have derived in the previous page of the notes. So, I will pick it up from here, that del U del T is effectively epsilon times del UA del T. So, next we appeal to the momentum equation, which we had written it here. So, this momentum equation I am bringing it again here, and now what I will do is I will keep substituting the form of density in its mean plus the acoustic or the fluctuating form. Du dt is already known to be epsilon del UA del T, and finally, on the right hand side we have gradient of mean pressure plus epsilon times acoustic pressure. Now, what we do is that we again from this equation look at what happens at each order. So, at order 1 we include those terms which do not have any effect of epsilon, that gives us gradient of P m to be 0. So, this means that the gradient of the mean pressure is 0. That is actually no surprise, because you will recall we have neglected the effect of any mean flow. Since the effect of mean flow is neglected, it is but natural that the mean pressure gradient has to be 0, because remember, if there is a mean pressure gradient, there has to be a mean flow accompanying that part. But now, since we are ignoring the effect of mean flow, we are treating that the medium is essentially quiet, there is no mean flow. So, therefore, mean pressure will not bother us. So, the gradient of mean pressure will be 0. So, we will usually not worry about this order 1 equation at the acoustic level. This is what will give us the mean flow effects, if at all it is there. Here we choose to ignore the mean flow effects. So, therefore, it is not to our interest from here on. Next, if we collect the terms of order epsilon, we get to see rho m del U A del T on the left hand side, and that must be equals to minus gradient of P A. This is what happens at order epsilon. There is also one more term at order epsilon square, which would read as rho A del U A del T. But we understand that order epsilon square being small, we will choose to ignore this effect. We are only going to look at equations at order epsilon. So, the equation at order epsilon, as we have written, is this equation. So, this equation is basically the momentum equation for our acoustic case. Please understand that this is a simplification to the Euler equations or the general Navier-Stokes equation. Now, what we are reading as the momentum equation from here on in the acoustic case will be this, and this is what we will use correspondingly in the subsequent derivations also, but for now this is the final form of the momentum equation for the acoustic fluid. Okay. So, there are two equations that we have derived. A third equation will come from the thermodynamic process. So, the thermodynamic process states that the pressure and the densities have got to be related. So, the thermodynamic laws essentially relates the pressure of the fluid and the density of the fluid as the compressible flow process is taking place. Now, using Taylor's theorem and treating this as any obvious function, nice and smooth and continuous, we could write this as P minus P 0 is equals to dP d rho evaluated at the mean quantity into rho minus rho m. m is the subscript for the mean quantity. Sometimes in some books it is just called 0, but we will use the subscript m for the mean quantity. So, the value of the pressure about the mean point can be obtained in terms of the value of the density about the mean point, and the functional relationship between the two is just related by the gradient of the pressure with respect to the density. But then P minus P m is exactly the acoustic pressure. So, P minus P m, if you recall, is epsilon P a. So, that must be equals to d P d rho into epsilon rho a. So, similarly rho minus rho m by our definition is epsilon times rho a. So, what we have got as a result of this thermodynamic analysis is that the acoustic pressure is related to the acoustic density through this relation, right. We will call this gradient dP d rho evaluated at the mean conditions as c square. Okay. We will see that c eventually will turn out to be the wave speed, but that discussion we will have it probably in the next lecture. But at present we are just assuming this quantity to be c square, and let us see where that takes us. So, now what we have is P a is equals to c square rho a, right. So, the acoustic pressure is related to the acoustic density in the above manner. So, we have got all the three ingredients in place: continuity equation, momentum equation and the thermodynamic process. What remains is just to do a few simplifications. So, the simplifications will be in the following manner. If you recall, the equation 1 that we wrote down for continuity equation stated the following, that this is the equation 1. So, equation 1 I will just write it once again: del rho a del t plus rho m del dot u a is equals to 0. And similarly, this is basically equation 1. So, now using 3, what we have is rho a is equals to 1 by c square P a, right. So, therefore, we have del P a del t 1 by c square plus rho m del dot u a as our equation of interest. And similarly, if we now look at equation 2, what we get was this. So, this equation 2 I will rewrite again, which gives me as rho m del u a del t is equals to minus del P a. Okay. So, this equation I will take divergence of this equation. So, taking divergence of this equation, which means I will just do a del dot operation on this equation, okay, or maybe I will do that in the next step. So, taking divergence of this equation. So, this equation can be rewritten as rho m del u a del t plus del P a, the left hand side of it. So, now I want to take divergence of it. So, I will give del dot, and that must also be equal to 0. So, therefore, what we have is rho m del dot del u a del t. Remember, rho m is a constant in space and time. So, the divergence operation has got nothing to do with rho m, it just comes out, and del dot del P a is del dot del is the Laplacian. So, we will get del square P a, that must be equals to 0. Now, in this equation we take time derivative once again, we take del del t of this equation once again. So, when we take del del t of this equation, what we get is the following: 1 by c square del 2 P a del t 2 plus rho m del dot u a, and this guy has got to take a time derivative upfront, right. Now, look at these two equations. So, this I will call it my equation 4 and this I will call it my equation 5. Look at these two equations, you have the same term sitting here. These two terms, this one and this one are just the same. The order of the differentiation process can be interchanged. First you can take the time derivative and then do the divergence, or first you can take the divergence and then do the time derivative, both will give you the same answer as long as you are dealing with nice and continuous functions. So, these two equations I have sometimes mistaken the missed the sign for the vector, please bear with me on that, but now that I have corrected it, you can understand these two terms as same. So, therefore, if we take a subtraction between these two equations, so subtracting 4 from 5, we can get to this equation 1 by c square del p a del t taken twice is equals to del square p a. This is the acoustic wave equation. So, acoustic wave equation is the equation del square p a, which is on the acoustic pressure, is equals to 1 by c square del 2 p a del T 2. Since from here on we will be always dealing with acoustic pressure, we will not be dealing with mean pressure. So, without loss of any clarity, we may as well omit this subscript a. The understanding would be that when we write P without any subscript, it essentially means that it is the acoustic pressure, because we are not interested in the mean pressure in this course at least. So, therefore, the acoustic wave equation will be given in this form. In the next class, we will elaborate more about the properties of this acoustic wave equation, but that is it for now. Thank you.